Hello everyone, I'm Rong from Nanjing University. It's a great honor to be here to present our work, Adaptive Online Cache Capacity Optimization where Lightweight Working Set Size Estimation at Scale. This work is jointly done by people from Nanjing University, Alluxio Inc., University College London, Meta Inc., and Princeton University. Nowadays, the caching layer is widely adopted for distributed data-intensive frameworks. For example, in Presto, they read data tables from cache layer instead of from the on storage to accelerate their data querying performance. Then the Spark and the Flink, they read data files from the data cache layer instead of from the data on storage to speed up the data file processing performance. However, allocating the right amount of data storage can be non-trivial. On the one hand, excessive resource unnecessarily will increase the cost. On the other hand, insufficient capacity will decrease the performance. Some studies have reported that dynamic online workloads make this problem even more challenging, particularly when operating the Presto deployments. We introduced Alluxio as its caching layer and observed a high cache ratio. It is important, however, it's unclear to us based on the existing cache metrics. We can hardly tell if we can reduce the cache capacity of the Presto servers while maintaining the higher cache hit ratio. There are many challenges in solving this problem. The first is estimate the working set size and the item repeated ratio online with little resource and proven accuracy. The item size can span over 8 or 9 order of magnitude in the production environment. And the inaccurate tracking items such as sampling may lose critical items, which may cause a huge drop in working set size of the estimation. And the amount of the data accessed in the time window can be quite large. It would be very time inefficient and space costly to store and calculate the item information online. All this causes the complexity in working set size optimization online. Okay, and the second challenge is how to achieve good scalability in high concurrency scenarios like multiple threading. It is common for real-world applications to access data concurrently. As the number of the threads increases, the consistency and efficiency of concurrent data access issues will become obvious. The third challenge is how to judge the cache status under various scenarios with cookie, which is the name of our proposed data structure. And it is non-trivial to tell whether the cache is overloaded or unused at the moment due to the variety of the working set size and the cache friendliness of the applications online. And there have been a lot of existing works. They can be mainly calculated into three classes. The first one is the ML-based approaches. They train machine learning models with historical data offline, but it can hardly adopt the dynamic online workload scenarios. The second is the MRC-based methods. They explore the optimal cache size by generating a missing cache curve, which is short for MRC. But it might be inaccurate for variable-sized item. The third is the window-based approaches. They estimate the cardinality of items in a sliding window, but it can hardly compute the accurate total size. In this paper, we first designed a data structure which is called a cookie here. And a cookie is a data structure mainly has a table called hash table. which has multiple fixed-sized buckets, and each bucket has several fixed-sized entries here to store the items, and each entry it has 4 fields to track an item's information. Also here we have 5 counters of atomic counters here, including working set size, repeated item number, total items number, and repeated item size, and the total item size. They are all high-level global metrics. And inside an entry or item, there are 4 important fields. The fingerprint here is a sustained representation of an item, and the clock represents the freshness of an item. The size is the encoded size of each item, and finally the payload. In payload, it can store the accurate information of an item. There are many important operations in cookie, which is the name of our proposed data structure. And for example, in item insertion operation, first cookie computes the fingerprint and the 2 buckets of a given item. Next, it searches for an empty entry into the 2 candidates buckets. If successful, cookie stores the item's fingerprint and the encoded size in that entry and initializes the entry the clock value to max age. Otherwise, it relocates other entries iteratively until it finds the empty entry. Specifically, cookie can find a cookie path in the hash table. The cookie path starts with a candidate bucket and ends up with an empty entry. Cookie performs the insertion by moving the items along with this cookie path. Cookie path here. Okay, and there are also an important operation in cookie called aging. This is because cookie needs to support removing item or entries by the item deletion here, and we can also use the aging operation to reduce their clock number. The cookie deletion method first looks up the candidate buckets. Then it removes the entry which matches the fingerprint. This figure shows that this figure here shows an aging example. For items X and Y, here we can find that here X and Y, and the aging operation decreases their clock value by 1 from 3 to 2 and so 1 to 0. But for the item 0 zeta, whose clock value was already 0, and for it will be removed directly. Cookie use this method to remove the stored items in the data structure. Actually, besides the background aging, we also proposed a light-weighted concurrency control strategy called optimistic aging here. It can automatize the aging operation into insertion operations in cookie. It brings 2 main advantages here. First, the full aging task is split into multiple minor aging tasks, making the sliding window moves more smoother. Second, since fewer entries needed to be checked in the background aging, it reduces the locking contention with the background aging. Based on cookie, we can design a cache capacity online tuning mechanism. We call it the adaptive cache capacity tuning framework, and Apart from the existing catch metrics, such as the catch space size and catch hit ratio, we can also use the metrics provided by cookie, such as working set size, item repetition ratio, together into the catch system metrics. And by comparing the metrics, we can find that the catch status can be judged. For example, the workload catch is unfriendly, and the catch system is now overloaded, or the catch system is still underused. Based on the catch status and the metrics in cookie, the catch space size can be appropriately tuned up and down online. The proposed adaptive catch capacity tuning mechanism can be integrated with Presto and Alluxio. We implemented the cookie in Alluxio client to track the local catch access. In addition, the implementation of the proposed adaptive catch capacity tuning mechanism in file reading is similar to the one here in the table query. They all embedded the cookie, this tiny data structure, into the Alluxio client part, and to control and guide the local cache capacity to be better be used. Okay. Next, we will introduce the evaluation performance of cookie and the related upper layer systems. First, we will evaluate the accuracy of the working set size and estimation. Here we compare the approaches called MBF in Alluxio and the clock gauge, sliding gauge, and the swap. The working set size here we used the dataset we used here are the Twitter trace and the data trace from Microsoft. From these two figures, we can find that cookie and cookie OA, which is cookie with optimistic aging version, they can both achieve much better ARE performance. Okay, which means the average rated error of cookie and cookie OA is significantly lower than the existing other approaches. Then we evaluated the performance of the stability during working set size assimilation. Here we compare cookie and cookie OA with MBF, clock gauge, and sliding gauge. And the data trace we used here is MSR trace. And here we can find that the relative error is much more stable for cookie and cookie OA than other approaches. This is because cookie can be can use the time window with more fine-grained item tracking here, so the relative error is much less, and they can achieve the most stable estimation results here. Okay, and then we evaluated the end-to-end performance in table query in the system that use cookie. And the system we run on a cluster of a Presto cluster with 5 workers, and the Presto is deployed on the Alluxio cache layer, and the Alluxio client is embedded in with together with the cookie here. Now we can find that cookie can achieve nearly the upbound cache hit ratio, which is the similar as the 10 gigabytes. But the cookie also needs to use around here 20 much less the cache spaces here. And also it can reduce the query latency from the figure B we can find, and with much less cache size. So this is very space efficiency and achieves good query performance. Then we evaluated the end-to-end performance in file reading. We use the YCSP as the dataset here, and we can find that cookie can still achieve the upper bound of the cache hit ratio, and also with much less cache size used, and so it can improve the cache utilization of the file reading to reach higher throughput. Then we evaluated the performance of the missing ratio curve generation by using cookie and existing methods. We also use the Microsoft trace here because it is very representative. And we compare cookie with the widely used cutting-edge system RARCM here. The figure shows that the accuracy of cookie in MRC generation compared with MIRCM, and we can find that cookie reduces the MAE. This is because that cookie can better support variable sized item. Moreover, IRCM estimates the reaccess ratio to compute the reuse distance, which is inaccurate. In addition, cookie achieves comparable throughput with IRCM in experience. Overall, cookie costs less memory and generates more accurate MRC than IRCM. Finally, we will introduce something we find how cookie can help the real world system in our practice. Okay. This figure shows that the performance of the query workloads over 1 day of a Presto cluster. It is showing the realistic cache hit ratio, short as CRH here, and the item repetition ratio, short as IRR here. And they are all estimated by cookie. It can be seen that the IRR is much higher than the CHR of the cache between the 19th hour to the 16th hour to the 19th hour here. So we can find that there is an opportunity to introduce the cache capacity based on the estimated working set size during the above period to improve the whole cache hit ratio. Okay, finally, I will conclude this work. And this work is an adaptive online cache capacity optimization where lightweight working set size estimation at scale. We mainly bring four contributions. The first is a lightweight and accurate working set size and item repetition ratio estimation. The second is the fine-grained concurrency control methods, which we use the optimistic aging and the segment lock techniques. The third is the adaptive online cache capacity tuning framework using cookie. Here we use cookie together with the existing cache system to tell whether the cache system is unused, is overloaded, or the application is fundamentally cache unfriendly, to tell the system online to tune the cache size. Finally, we also conducted extensive evaluations and applications in practice to show the effectiveness and how to use the cookie in the environment, in the applications. And that's all for the old talk. I'm sorry I cannot be here to present the work, and I do it virtually online. And if you have some questions, you can send me some emails, I think. Thank you.